You are one of the companies that I think is just going to be insane. So I'm like super excited about everything that you're building. It only makes sense to start off the podcast with obviously the first person. So there we go. So look, tell everybody what you're building, and
Sure.
let's just get to it. How the hell are you going to build a superconductor? Let's start with
Yeah, sure. So first of all, let's define a couple things, right? So before we get into superconductors, I want to talk about Richard Feynman. So Richard Feynman is the father of quantum computing. In the early 1980s, he realized that nature is quantum mechanical. So whenever we're interested in understanding the physics of, let's say, the brain, biochemistry, new materials like, let's say, plastics, semiconductors, all of these things share one thing in common, and it's the fact that to describe them properly and to simulate them, you need to be able to simulate quantum mechanical systems, since that's what all these materials emerged from. And so in the 80s, he came up with this ingenious idea that in order to simulate nature in these quantum mechanical systems, you need a computer that's also using quantum mechanical systems in order to simulate other quantum mechanical systems. And so that was the birth of the quantum computer. And so these quantum computers are inherently, they were made to simulate nature. That was their initial purpose. Now people are finding other very clever applications for them. But so what ReactiveQ is doing is taking Richard Feynman's dream literally and trying to manifest it into the way that he envisioned it. So what we want to do is to be able to simulate materials before you spend millions of dollars or billions of dollars researching them, and several years and decades in making those materials. We would like to be able to simulate them instead, so that we know ahead of time whether this material is worth making or not. Imagine how much that would accelerate, let's say, the next generation of battery development or semiconductors or superconductors, when you can suddenly discover these things within moments rather than years.
that's amazing.
Thank you.
You're using quantum computers to be able to discover these in moments instead of years.
Exactly. You got it. That is the end goal here. And so our target materials, so our platform, the thing that we're building based on quantum computers and quantum computing platforms, we want to be able to discover any new material or any sort of, let's say, unique combination of atoms that have never been seen before. So that could apply to drugs as well, right? And so what we want, though, is the target material, the dream material that we want to discover is a room temperature superconductor. That would be sort of the Hail Mary of material science.
Okay, so before we get into the superconductors, let's just start off by saying, like, why does quantum computing make more sense than any other computers to simulate nature and find the correct like composition of atoms to make these superconductors or any materials? Why is quantum the best way for new material design?
Great question. So there's two main reasons why quantum computers are best made for simulating nature. The first one is what I call the exponential scaling problem. So let's take, for example, a group of atoms. They're all entangled. So let's say 155 electrons, and these 155 electrons are entangled. Most materials, most very, like, let's say any material you're interested in, let's say a titanium alloy, will have trillions of electrons that you want to describe, right? But let's just start with 155, and you'll know why I picked that number for a reason. So if I wanted to keep track of the quantum state of 155 electrons, I would need 2 to the 155 classical bits to store that state. And the reason why is because for every body you have and every entangled body you have, or entangled particle, we need 2 to the n classical bits to represent that. So if I have, let's say, 10 electrons or 10 quantum particles and they're all entangled, to keep track of their overall quantum state, I would need 2 to the 10, and so on, classical bits. So if I have 155 electrons, I need to store them in 2 to the 155 classical bits. But here's the problem. According to the Department of Energy, um, if you were to count every atom on planet Earth, including our atmosphere, the oceans, and all that stuff, you combine it together, that would make 2 to the 155 atoms. So even if I turned the entire planet into a supercomputer, I wouldn't be able to store the quantum state of just 155 electrons. And so quantum computers don't have that problem. Quantum computers would just need 155 qubits instead of classical bits to represent 155 electrons. It's linear rather than exponential. So now you can suddenly do things that are literally impossible by today's computers, which is, storing this quantum state. Then,
so what was one possible thing? Oh, sorry, go ahead.
Yeah, sure. So yeah, I'll touch on that for sure, because that's where Google's quantum supremacy announcement comes in. But so the second thing that quantum computers can do that classical computers can't, and quantum computing platforms in general, is they can model quantum effects like quantum tunneling, right? So for example, quantum tunneling was one of the things that drew me to this field, actually, was that you could have these weird scenarios. In the classical world, so the world that you and I are used to, right, where these macroscopic bodies and we're subject to just the laws of classical physics. That's what we observe and what we interact with. It's all based on Newtonian physics and Einsteinian physics. All of that is based on, again, the classical world. And in the classical world, let's take a ball. If I threw a ball right behind me, it would bounce off the window, right? That's what we would expect it to do. However, with quantum tunneling, it's a very strange phenomenon. When you have a particle, let's just say one electron or any group of particles, what they can do is do something called quantum tunneling. So instead, if I were to shrink this ball down to the size of an electron, and I just threw it behind me, there's a small probability that that ball will tunnel through the wall and end up on the other side, as if that wall was never there. It's a lot like Harry Potter, where you have this ghostly train coming through the wall. And so what quantum computers can do is they actually leverage these physics and principles. And so they can simulate other systems that are also using that.
So what was one of the first things that quantum computers did that was impossible by normal computers?
So the first thing that they did was something called quantum random number generation. Now, this was an announcement made by Google in 2018 when they achieved something called quantum supremacy. So there's two milestones that I think are worth defining. And I'll give you an example, by the way, at how fast this field is developing. I joined the space about a year before this milestone was hit. And when I had joined it, there was this idea of achieving quantum supremacy, which the field was interested in. Quantum supremacy was a point at which a quantum computer could perform an algorithm or a task more efficiently and faster than any classical supercomputer on the planet could do. And so it was believed that that milestone would be achieved in several years after 2018. We were expecting to hit it mid-2020s, conservatively. But it ended up happening less than a year after I joined the field. And so that milestone was hit by Google. What Google was able to do was they took 53 qubits and they applied these single gate and single qubit gate and 2 qubit gate rotations. So if you were to visualize your quantum state as a vector, it's really an array in what's called the Hilbert space, but you can think of it as an arrow in a very complex high-dimensional space. So if you were to start with that starting quantum state, what Google did was they were able to rotate that state randomly using these quantum circuits that they had created to the point where the random distribution that we measured at the end, if we were to replicate that probability distribution, it would require a supercomputer several years, up to 10,000 years, to replicate that distribution. And they did this in seconds. So that was like the first big milestone that the community hit. Now the field is going towards, we're aiming for the second milestone, which is something called quantum advantage. That's the point at which quantum computers perform or give an actual industrial advantage or commercial advantage.
That's what I was going to say, because generating random numbers isn't commercially super helpful, right?
Yep.
Now we're getting into the commercial applications of quantum.
Exactly.
So first off, before we get into the commercial applications, let's just say, what enabled Google or any of these quantum computers? How did we, instead of waiting until 2025 in the middle of the decade, what actually advanced them much faster than everybody was thinking? Was there like a hardware development, or what was that?
So that's a great question. Really what it came down to was immense engineering expertise paired with the best physicists in the world who were trying to create this.